Before we discuss the wavelength and wave speed, let's examine the direction of wave propagation. To do this, let's first consider a simple example. Suppose we have a straight line y of x equals 2x with a slope of 2. If we replace the argument x in the y function with x minus tau, where tau is a positive number, well, the line moves to the right or to the left. It should be easy to answer. The line will shift to the position x equals tau. As a result, the line moves to the right. Now let's consider a traveling voltage wave on an infinite line, represented by the phasor v of x and related to position x. Its time-domain response is a times cosine beta x minus omega t for the voltage wave propagating in the positive x direction, and b times cosine beta x plus omega t for the wave propagating in the negative x direction. Since we are dealing with an infinite line, we can assume that the wave will continue to propagate endlessly in the positive x direction after entering the line. It won't encounter any obstacles, and therefore there will be no wave reflected back and propagating in the negative x direction. As a result, we can ignore the term related to the negative x propagation in v of x for now. We will examine its significance later when we discuss finite length transmission lines. For now, let's consider only the first term, a times exponential to negative j beta x in v of x, which corresponds to a times cosine beta x minus omega t in v of x comma t. When t equals 0, the omega t in a cosine beta x minus omega t is also 0, and the value of the wave is equal to a times cosine beta x at this time. If we start from the initial position x0, the value of the wave at that position is equal to a cosine 0, which is the peak of the wave. When 1 second has passed, that is t equals 1, the wave angle will increase by omega radians. At this point, the value of the voltage wave is a times cosine beta x minus omega. The wave peak, a cosine 0, will move to position x1, which is equal to omega over beta, since beta x minus omega must be equal to 0. Similarly, when t equals 2, the value of the wave is a times cosine beta x minus 2 omega, and the point a cosine 0 will move to position x2, which is equal to 2 omega over beta, since beta x minus 2 omega must be equal to 0. More generally, when t equals tau, the value of the wave is a times cosine beta x minus omega tau. The point a cosine 0 will move to position x tau, which is equal to tau times omega over beta, since beta x minus tau times omega must equal 0. We can observe that the wave travels in the positive x direction as time increases. We will examine the wave in space and time in greater detail later on. Okay, now we know that the wave propagates on the line. We want to know how fast it propagates, right? So next, let's determine the wavelength and wave velocity.